Be able to view the recording. All right, well, again, welcome to the first in a series of webinars all about real instruments, real data, and real science. We're going to be talking about investigating exoplanets using online telescopes, and specifically the MicroObservatory Robotic Telescope network that we operate here at the Harvard-Smithsonian Center for Astrophysics, with funding from several different organizations. And in particular, for this webinar series, we have support from the Arthur Vining Davis Foundation, who are very interested in how teachers use our instruments and use it for engaging students in authentic science. We have funding from the National Science Foundation, and we have funding from NASA through its Universe of Learning consortium. And also on the line as panelists with me, Emma Marcucci is a scientist from the Universe of Learning program at Space Telescope Science Institute. And again, Erica is an education specialist here on the MicroObservatory team, and through the webinar series will be your go-to contact person, often letting people know of opportunities and events. So we're going to talk about using the MicroObservatory robotic telescopes. It looks like there's about a third of folks on the line who had never used MicroObservatory before, but are familiar with exoplanets and interested in using them. These are small 6-inch aperture ground-based telescopes, and they are for the public and for students and teachers. And we have a number of portals for their use, but specifically for exploring exoplanets, we have 2 portals, one of which is called the Laboratory for the Study of Exoplanets. We call it ExoLab for short, and it's optimized for teachers and classrooms, primarily aimed at high school students, although we have quite a few undergraduate classrooms, Astronomy 101 classes using the ExoLab with faculty and students. And then another portal is the DIY Planet Search portal, which is basically for everyone else, for interested individuals, for people who don't have access to their own telescopes, for informal educators, those of you who may work in museums or an after-school situation, or even those of you who are teachers but want to encourage your students to do more after that you do the ExoLab in the classroom. DIY Planet Search allows you to really join the community of exoplanet researchers by continuing to detect exoplanets and investigate their characteristics. So those of you who are using DIY Planet Search, a little later we'll talk about you can also host groups, how to do family workshops using that interface. But first, I want to give an overview of where we're going to go in the next 50 minutes. I want to give a brief science background about exoplanets. We're going to talk about what you and your participants can do with these MicroObservatory portals. We're going to show some examples of participant results, and you're going to learn today how you can detect a planet today, if you want, because I've gathered research data from last night, and it's ready for you to analyze to see if there's evidence of a planet there. And then we'll end with some Q&A and a preview of what's next with our next webinar on Thursday, and then we have 2 more next week. We also have an online discussion group, which we'll introduce you to at the end of this webinar as an opportunity to follow up with some asynchronous discussion and find out more about these resources. So our science background, until 25 years ago, maybe it's 28 years ago now, we didn't know how many other planets there were other than those in our own solar system. But now, in fact, as of today, the NASA Exoplanet database lets us know there's 3,726 confirmed exoplanets discovered in some 2,700 systems. So some other solar systems have multiple planets. We know from research, particularly with NASA's Kepler mission, that on average, when you look up at the sky, on average, most stars have a planet around them. And in fact, we also furthermore know that about 1 in 6 planets are Earth-sized. As for habitable zone planets, which is one of the things lots of people are really interested in, to date, there's a few dozen that have been discovered in their habitable zones, maybe 50 or so planets. There's a lot of Earth-sized planets that have been discovered, almost 1,000, and an incredible diversity of exoplanets of all sizes. Just to give a little background on how this explosion of discovery has happened, I'm going to actually bring in the live website into my Zoom window here. This is the NASA exoplanet site, exoplanet.nasa.gov. And this little interactive demonstrates 5 methods for detecting exoplanets. And the first exoplanets in 1992, a planet was found around actually a pulsar, so it wasn't of interest to a lot of folks because pulsar doesn't give off much light for life, but it was the first planet found. And in 1995, the first planet around a sun-like star. Those were found by this wobble method, or radial velocity, which depends on getting spectra of the light of a star and the fact that the gravity of any planet orbiting its star actually tugs on the star, just as the star's gravity is actually pulling on the planet to make it orbit. So that if you look really closely at that spectral signature, you look really closely at the light from a star with a planet around it, when the planet is tugging the star towards Earth, the light is blue shifted, and when the planet is tugging the star away from Earth, the light is red shifted. So that was the first method used, but in fact it's not the most frequent method through which we've discovered planets, because the transit method, you can see here, 2,900 of those 3,700 planets have been discovered through the transit method, and that's what we're going to talk about with MicroObservatory. In this method for detecting exoplanets, you look for the dimming of light in the brightness of a star as the planet goes by. And this model on screen is pretty simplified, as we'll find when we start to look at real data from telescopes. But from that dip in the light, as the planet actually eclipses its stars, you can not only tell that there's the planet, you can tell the period of the planet, you can tell how big it is, and we'll talk about that. That's the method we're really going to focus on with MicroObservatory. So again, I encourage you to go to this 5 ways to find a planet website. We'll be posting that on this online discussion board that you'll have access to it after this webinar, to explore the other methods. But we're going to talk about primarily the transiting method here. So instruments on Earth and in space rely on this method of staring at stars and looking for dips in their brightness. Of course, the Kepler mission is the most productive transiting exoplanet finder so far, although just recently NASA's Transiting Exoplanet Survey Satellite, or Satellite for Survey Satellite test was launched, and this artist's depiction came from a press release just the other day. TESS is going it just passed the moon to get into its orbit for staring at stars. There's a lot of ground-based telescopes and small telescopes that are doing a lot of exoplanet research, and it's that small telescope research that gave us the idea that we might be able to use MicroObservatory to detect exoplanets, and indeed we can. So that's what we're going to talk about. Another piece of the research, of course, is that all these worlds that Kepler has discovered and other NASA satellites like Spitzer and Hubble and other ground-based telescopes are not like ours. There's this incredible variety of exoplanets. This artist's illustration here is from the press release about the system called TRAPPIST-1. It was a Belgian group that discovered this, thus the TRAPPIST name. But the work from the Spitzer telescope really helped identify that there were 7 planets going around the star. So this was a solar system with lots of planets like ours, but all of those planets were within the orbit of Mercury, and the star here is much cooler. Because the planets are all so close together, if you were on one planet, as you are in this picture, and you looked up in the sky, some of your planetary neighbors would actually be large in the sky, like our moon. They are very close, and you'd actually see them, some with phases, as you see in this image. So amazing diversity of planets and we can characterize many features of these planets, and we can imagine many features that we have yet to be able to find specific evidence for, but that's in the future. So these are the instruments you'll use, and in fact you'll use one of them this is our site in Amado at the Florence Whipple Observatory in Arizona, and one of these telescopes, we've named it Cecilia after Cecilia Payne-Gaposchkin, a famous female scientist in history. Anyway, our telescope Cecilia, which is on the right here, is dedicated to observing exoplanets every night, almost every night. And in particular, because these are small telescopes, we have to look for planets that are pretty big compared to the size of their star in order to be able to detect that dip. So we study hot Jupiters, which in fact we're learning a lot from hot Jupiters because they are easier to detect, easier to get light from, including spectra. So hot Jupiters are where a lot of the research is happening, even though Earth-sized planets are also of big interest as well. So we're going to use the MicroObservatory Telescope. We are going to, as we saw earlier, the brightness of the star will change as the planet passes in front of it. So we need to know kind of when that planet is due to pass in front of its star. And based on that, we use the telescope to take multiple images of the solar system. Then those images come back the next day, and last night we took images of 2 hot Jupiters. We took images of a system called TRES-3, named after the small telescope system, the Transiting something Exoplanet Survey. Emma, if you can remember that, maybe you can type it in the chat box. And we also we also took images of WASP-43, which is from the Wide Angle Survey of Planets group. So WASP-43. So I'm going to show you today how to measure the brightness of those images that came back from the telescopes. And our portals, both the ExoLab and DIY Planet Search, allow you to display and interpret your results as a light curve, or that graph of the dip over time. And from that graph, you can deduce quite a bit about the planet, including its size and its orbit. So I'm going to talk about the ExoLab first, our portal for teachers. It has more elaborate features and teacher guides, and helps you really understand what the telescopes are doing before we use our DIY Planet Search portal. I'm going to drag a web window in here. Let's see, here we go. All right, so you access all our portals at the website microobservatory.org. So I'm going to click on the ExoLab, and I'm going to log in here with a name that's probably not familiar to some of you, but anyway. Okay, so I am logged in to the ExoLab as a teacher. If you you sign up for ExoLab by you can sign up and register the number of students that you have in your class. So I'm going to go to the lab. Again, the ExoLab has many resources for teachers, including lesson plans, calendars for the upcoming months, some video tutorials. But let's go to the lab. And again, here's another difference between the two portals. ExoLab runs in Flash, so you need a Flash compatible browser. I'm going to allow that. The DIY Planet Search portal runs in HTML5. So in the modeling lab with students, you have a chance to talk about the model that's behind this idea that the light from the planet is going to dip, and you can page through information about that. And in fact, you could ask your students I'm actually physically dragging this. I'm making a prediction of what I think is going to happen here, right? And so this modeling lab allows you to kind of explore what you think ought to happen to the brightness of a target star. Of course, remember, this is a model, and in real life, when you take images of stars, what you see is more like this. Not like this, but like this. Any star on your telescope detector is really a single pixel. You cannot make out the disk of a planet. The only thing you can make out is the brightness of that star. And so it's by measuring the actual brightness that you can determine whether there's a planet going around it. So to take images, again, as I mentioned, we have on average a hot Jupiter available every night. Tonight we have WASP-10. You can see we've got a couple of dozen target stars, and so I'm going to request WASP-10, and you see that we're observing it over a period of 4 hours here. And so I'm just going to, as a teacher, once I request a single time slot, this is going to, yeah, okay, that's all right, I can do this. Once I request a single time slot, the whole observing run of images winds up in my class's image lab. And so I'm actually not going to take that yet. I'm going to go to the image lab because yesterday I did this. I took an image of, I'm in the wrong account. Not there. Hang on, I'm going to log out and log in to my workshop account. Because in this one, I have created 30 sub-accounts, which are you guys can use. So if I go to the image lab and I show my list, yes, here we see I have my images, a list of hundreds of images. These are all from last night, all taken over a period of about 4 or 5 hours. And then another set of images that were all taken over a period of about 3 hours, maybe 4 hours. So we actually squeezed in 2 observing runs last night. And the one I'm going to encourage all of you to try out and try it out tonight is this TRES-3 set of images, okay? Every image coming from MicroObservatory has a name that actually tells you exactly when it was taken. So all these numbers are telling you it's TRES-3, taken in 2018 on May 05, 21st. That's today, but this was taken last night in Universal Time at 08/18/12 in Universal Time. This will all be important later on as we go through the webinar series. So here's what an image coming back from the telescope looks like. Right? How do you know which one of these dots on the screen is our target star? Well, I'm going to help you find our target star. I do want to let you know, for those of you who are able to manage actually looking at the website live while I'm demonstrating, you can, are you ready to do that, or shall I do that? Yeah, so you can log in as teacher 1, teacher 2, teacher 3, teacher 4, and perhaps you can look on the attendee list and kind of see where your place is and count down and use that number. So if you you just use the username teacher digit 1, teacher digit 2, teacher digit 3. So and your password in my account here will be teacher dot digit 1. So if you're first on the list of attendees, that's I have Daniel Walsh here, you'll be teacher 1, teacher dot 1. Jackie, you're fourth on the list. You'll be teacher 4, teacher dot 4, or something like that. So so if you want to follow along, that's how you do it. This could be very exciting, because if any of you are doing this, you'll see what happens as I'm doing it. Okay, so here's my image. I don't know where TRES-3 is in this star field. ExoLab has a finder chart here where it says locate target star. And you see it pop up. I'm going to hide it. It pops up. And so you either have to be good at finding patterns. I see here that there's a parallelogram for the target star. This is TRES-3. That's the star predicted to have a planet going around it last night sometime. And then these two, labeled C, are comparison stars. If we only measured the brightness of our target star, we wouldn't know if it dimmed because clouds went by or because of some other reason. Maybe it's just variable. So we compare it to 2 comparison stars. So you might look for this parallelogram, might be a little hard. I actually see it right there, but anyway, if you don't, the ExoLab actually allows you to overlay this finder chart, and you can even do your measurements while it's overlaid. So target star. I'm going to hide the finder chart though, because I think it obscures what I'm doing here. So I'm going to go to page 4 here. And here, if I move this up on the screen, as I move my cursor around the screen, you should see all these little numbers in the magnifying glass at the bottom of the screen. Every pixel in this image is measuring the amount of light that hit that pixel. And so when I go to a big star, like this one, you can see a bunch of the middle pixels of this star are at 4,095, which is the saturation value. That's the maximum our detector can register. And this star, there'd be too much light for us to get good measurements from it. But if we go to this star here, you can see the brightness values there. So if I measure my target star and click, I have a problem in that I'm measuring not only the signal coming from the sky, but the signal coming from the instrument, from the telescope itself. So as you see in this, it says you have to subtract the dark image, and that's what the subtract dark is about. So I have to go back to my list, and you see for every observing run, if you did it from the night before, your dark image will be right at the top. So I click on that, and here you can see again all the dark pixels are in the 300 values, and I'm going to subtract the dark from itself. Click. Now notice that the magnifying glass is reading 0. I've subtracted an image taken by the telescope with the shutter closed, and I'm going to subtract that from all those signal images with the image of the star. It's kind of like calibrating a scale or zeroing a scale before you measure the weight of something. The instrument itself, you want to calibrate your instrument, and in the case of a digital telescope, it's contributing a signal just by virtue of being out there in the Arizona heat. So we subtracted the dark image. So let's go back to my list. Go back to an image here. And again, the target star is here. And now you can see those values in the magnifying glass are much less. Rather than 300, the dark sky value is around 36. The star itself is 482, 299. So I'm going to put my circle looking at this magnified box in the upper right around my target star and click. So that's adding up all the pixel values that are in that magnifying glass right now. Then I'm going to do the same thing. I have to click in the box that I next want to measure. Click comparison star 1. I usually like to go clockwise just to be consistent. So I get that right in the middle here. Click. Then I click in the box to tell the computer I'm measuring comparison star 2. Click. But you notice every image also has a bunch of pixels of the dark night sky. So we need to further control that variable, because the sky itself isn't perfectly dark. It's not 0. There's some signal there. So we want to subtract the dark night sky. So to do that, as you see here, you measure 2 dark areas of night sky and we average them. I recommend that you choose your areas of dark sky near the target star. Other professional astronomers calibrate in a different way, but in our case, it helps to measure your dark sky near the target. So there's 1,492, and here's another area of dark night sky. Whoops, I need to click in that box. Another area of dark night sky. Now, I'm going to click on 9. This is the calculation to get the relative brightness of TRES 3 compared to the average of those 2 comparison stars. So I'm going to click calculate and record, and up here you see I get this relative brightness value of 0.9995. And what the ExoLab and the DIY portal does for you is automatically graph that value. So there's the value I just measured. You'll notice I also measured a couple of other points earlier before the webinar. I don't really see a trend yet. In fact, if I hit the class graph, it looks like some teachers have made measurements. Actually, I think I tried to be a teacher, but I think there's some others because I was never teacher 31. Whoever did that, Ra. Oh, Erica's assigning people numbers. Excellent. All right, great. So we have something that's kind of crazy here. I don't really see a pattern yet, but remember there's hundreds of images. And so it's not until you have hundreds of images that you will actually be able to start to see the data here. The nice thing is from the teacher's point of view, I can actually hover over the dots and see who made a measurement. So if there's a measurement that's really out to an outlier, we can check and see if it's a bad measurement. And in next week's webinar, we'll go over how to do that. So your assignment, those of you who want to explore the ExoLab and haven't done it yet, or even if you have, because on the next webinar we'll look at your data, is to measure a bunch of images of TRES 3 that are in your image lab here, that are in this show my list. Okay, so if you if we want to divide the images among the numbers here, I'll say whatever number you are, if you could do the last 2 digits here, at the last, or the hour digits, the 3rd and 4th from the end, measure all the images that have your number and the images that have your number plus 30. So if you are teacher 15, you're going to measure all the ones that have 15 and all the ones that have 45. If you are teacher 2, you're going to find there aren't any 2s, but there's something close. So you find the one that's closest. I don't see any O2s, but I see some O3s. So do O3 and then things at 33.
Mary, we've had a question that I think would be good to answer out loud. How many images do you need to be able to calculate a period in general? They've heard 50, but maybe there's more.
How many images to calculate a period? Well, okay. That's actually a really great question. All the stars that we look at with MicroObservatory have a transit duration. That's not their period. That's the duration of the transit, the duration of the time that the star is in front of it, that the planet is in front of the star, of a few hours, okay, of maybe 2 hours to 4 hours, something like that. But of course, that doesn't tell you its period, which is when's the next time that it's going to pass in front of its star. So the number of images to get the duration really depends on how accurate you want your data to be. The more images you can collect over that 4-hour duration, the better. MicroObservatory takes about 20 images an hour. And so typically we might have 100 to 120 images across that 4 hours of a transit. For the period, there are some ways to deduce the period, from the length, from the duration of a single transit. But what professional scientists really like to do is they like to, keep staring at a star and wait for the next transit, because that's the period, the time between two transits. And so MicroObservatory, of course, the problem with that is the next transit might be in the daytime and our telescope doesn't catch it the next time. So we give you tools in the teacher guide for deducing, and you have to make lots of assumptions. You have to assume that it's a sun-like star, and you assume that the star is the same mass as our sun, so that from the duration of the transit, you could deduce the period. So I'm not sure I answered your question, but there were two different answers to it. Okay, great. So let me show you some examples of data that has been taken with this. And actually, if I go to the data lab, I think my workshop. So here's what we've got so far, and we'll go over the data lab next week. This is enticing, although we don't know whether we have anything yet. In the data lab, instead of showing the graph where in the image lab we showed the graph, we showed the graph according to the time of night it was taken last night. In the data lab, we actually use the parameters that are actually already in NASA's Exoplanet database to graph those brightnesses, not against the time in Arizona, but in terms of hours from the predicted transit of that star. So here's our data from last night's TRES-3. It looks intriguing, like maybe we have detected a transit, but frankly, there's only one point. There's only one point where there seems to be a dip. These are all a little bit noisy. So you guys, as teachers 1 through 30, have to get that data between now and Thursday for us to check on this. But I'll show you, here's a star that I did a workshop for. Whoops, that one didn't come out. Let's try this one. Ah, yes. Here's data, and this is typically what data from MicroObservatory telescopes looks like. So doesn't look like that nice model, right, where you have this perfect line of a dip. It's kind of messy, but we'll go over that messiness and how you draw a conclusion from it next Thursday. Okay, so having given you the preview to measuring the images that come back from the telescope on the ExoLab, I want to briefly show you the same tools in DIY Planet Search and encourage all of you to make your own account in DIY Planet Search. So let's go back to that microobservatory.org, click on DIY Planet Search, And I have an account here, and okay, so you can just sign up and get your own account in DIY Planet Search. And again, we have a different, one of the nice things about DIY Planet Search, which is not true of the ExoLab. For the ExoLab, you can only ask for images in that telescope tool. You can only ask for images that are going to be taken that very night. Okay, you can't ask for them days in advance. You can't ask for them if they were already taken a while ago. But in the DIY Planet Search site, you'll notice it has some extra features because it's meant for interested individuals. You can have friends who do this with you. You can measure transits with a group of friends, and we'll show you how to do that on next Thursday, but I'll show you right now how to do it by yourself. Here, DIY Planet Search has a calendar online, and you can see that this is the 21st, and just like in ExoLab, because it's using the same telescope, it's using Cecilia out there in Arizona, the data that you can take tonight is WASP-10. So if I click Observe, again, images are being taken from 12 midnight through 4:12 a.m. Okay, I can choose any of those images, but I think if I just click on all hours, right now, all of our targets are 60-second exposures with a clear filter. We're hoping to do some follow-up on the test mission discoveries, and once we start that later this year or next year, we'll have different targets have different exposure times, but all of them are 60 seconds, a clear exposure. I clicked all hours, I click take image. It tells me I already requested this image. I did this earlier today, but it'll tell you. So let me go back to that calendar. And the thing, as I was saying, the thing about ExoLab is, oh, I'm interested in WASP-39 2 nights from now. I'm going to click that. I'm going to click all hours, and I want you to watch right here under user activities, under my little fish icon here. When I click all hours, 1, 2, 3, click. Whoops, I didn't, when I click take image, 1, 2, 3, click. There we are. So, so it tells me I have some new images pending, and here it tells me WASP-39, day after tomorrow, there's going to be 98 images requested. Okay, so that's how you request an image. You can use the calendar to hit observe, and to measure the brightness, you go to My Planet Search, which is kind of like the Image Lab. This is where all your images are contained, and you can see I've got, I just took WASP-39, so that's pending, right? I click that little down arrow. I just took WASP-10, that's not being taken till tonight, so that's pending. But I did take TRES-3 from last night, just like the ExoLab we did, and if I click that down arrow, I see a bunch of green check marks, which means these images are now in your account, in my account, and I can measure them. And so I can measure them in a number of ways. One is I can click right on the little eye to see them in the DIY measurement tool, or I can go to the DIY stream and go to the brightness tool. Either way will get me to the same place. So I'm going to go to brightness, and if I go to my images, I can see all my TRES-3 images here in a row. And I see that I made a measurement of one of them because it's got a check mark on it. So it keeps track of which ones you've measured. So I'll measure another one here. This is time of night in Arizona was 1:30 a.m. The time of night in England was 08:30 a.m. So again, I have to figure out where TRES-3 is. I don't know. In DIY Planet Search, your Finder chart is a pop-up PDF like this. And again, I'm looking for a little parallelogram and those two comparison stars, which are there, there, and there. There is a little video, a star finding tutorial to help you get good at that. That's one of the key things to get good at. And there's a tutorial on what I'm about to show you with regard to measuring brightness. It's the same protocol you use in ExoLab. Again, as I move my little circle that's going to be measuring all the pixels inside it, you notice that the values are in the 21,000s, okay, for all the pixels added up in that circle. Again, you want to subtract a dark image, and in this DIY portal, you do that by pressing the calibrate button. So notice right now, when I put my circle over TRES-3, that number in the box reads 23,952. When I press calibrate, now it only reads 3,760 because I've subtracted the dark image from this image. So again, in DIY, I click, I get my little circle right over the target star, click. Then I'm doing comparison star 1, click. Comparison star 2, click. Dark part of the sky 1, and I go kind of near my, there's that. And notice the dark sky is much less than the stars. That's good. And here's dark part of the sky 2. And then I hit calculate and record. Right now, our database seems to be taking a little time, like 5 seconds to make that calculate. There it is. So there's the calculation, 0.98. You'll remember that was in our last ExoLab. We got a relative value of about 0.99, but it was for a different image. So the two systems work the same. If I click on graph brightness, again, here's the image we just measured. And here's another one I did earlier. So that's how you make measurements. I can show you the typical results of people in both communities. And I'll do that right now, just before we end. So here is a map of all the people who are using DIY. There's a couple thousand. Some of them have published the results, and we'll talk about that on Thursday. But if you wanted to take a look at different target stars, here, let's see, we're going to do TRES-3 together. Let's see what, lots of people have done TRES-3. Something weird. Oh my. Okay. This is what happens when you ask your developer to work on something the day you have a webinar. Okay, so let's take a look at a recent one. Okay, does work. So here are the community data on TRES-3. This is lots of people's, if we get other users' points, this is lots of people's data of that TRES-3. And you see, we definitely see a dip there. If we look at some of these other stars, if I look at WASP 39, okay, this is a little messier. but you can definitely see a dip. It looks like something got really messy towards the end of the observing run. Okay, and you can explore. Here's WASP 43. I'll take a look at WASP 43. Okay, that looks a little messy as well. But this one, I think Martin is actually on the line here. Here's Martin's WASP 43. A nice job. And we'll talk more about some of the work Martin has done in exporting DIY data and doing transit fitting to that. And that's what we're going to be enabling in the next year to really follow up and publish your exoplanet results in the NASA Exoplanet Archive. So we'll be talking about that more later on in the webinar series, but that's an example of the data. So I want to just go back quickly to the ExoLab and show you some of the student community data there. Let's see, lab community results. And here again, here's TRES 3 results from students. Here is some HAT P36 results from a couple schools, and you can see individual schools by highlighting them. So with that, that's your introduction to ExoLab and DIY planet search, and I want to open it up for questions before we end. Are there questions that came in, Erica, that I need to get to or that you weren't able to? No. If you have questions, you can put them either in the chat box or the question and answer. And if not, we will be sending you all out the link to the recording of this webinar. Erica will actually be sending you a link to our online discussion forum. And actually, she'll send you that link, and I'll go to it now real quickly. And oops. You'll have a chance to introduce yourself to us on this forum, and we'll be posting the recordings here as well, although we'll send you a direct link to those recordings. And as we move through the series of webinars, there'll be more resources posted on this website as we learn about them from our various presenters. So with that, it looks like no questions have come in. I want to thank you all so much for attending our first in a series of webinars for Exoplanet Explorers, and we'll hope to see you Thursday. Thanks so much. Bye, everyone.